This is Jeff Goals. We're doing the second part of our lecture on nonlinear systems of equations. Here in the previous part we've looked at a recap of solution of linear systems and the characterization based on the eigenvalues. And then we re-examine the predator-prey equations by determining the critical points, linearizing the system around the critical points, and looking at the characterizations of those linear systems to evaluate the nature of the nonlinear system in the vicinity of the critical point. The second system we'll be looking at is the competing species system, another classic system, where we have two species and they're competing essentially over a resource. We have so you can consider, for example, two species of grazers. And species X, our first equation looks like this, equals X times K1 minus A1X minus B1Y. And our second equation is similar because they're competing, Y times K2 minus A2Y plus or minus B2X. So let's have a look at these terms. Now this is the way it's commonly written in mathematical texts, so don't confuse K with the carrying capacity. Here we have, if we multiply this through, our first equation looks like this, X dot equals K1X, so that's a growth term. That alone would be a growth term, exponential growth. And then we have minus A1 times X squared. So there's our density dependent term. Minus B1 times Y. So this is the interspecies competition effect term here. So we have Y having a deleterious effect on X, and X dot, same thing, essentially with different parameters. It may have a different growth parameter. It may have a different density dependence. Here we have, there should be a Y, and Y squared minus B2X. And there's the interspecies competition term in the Y equation there. So that's essentially what that looks like. So we have density-dependent growth, both equations, in the interspecies terms here, that couple them together. Without that, we just would have the logistic equation for two separate species. Let's put some actual numbers in. Do X dot equals X times 0.2. There's your growth. Minus 0.05X. So 0.05 would be your density-dependent term. Minus 0.02Y. And Y dot, this is from your lecture notes, equals Y times 0.1 minus 0.01X minus 0.02Y. Let me just rewrite that. Minus 0.02Y minus 0.01X. That way we have it written as first term being growth, second term being density dependence, and the third term being the interspecies competition term for both equations. So where are the equilibrium points of the system? Well, we can solve for that. Again, equilibrium occurs when X dot equals 0 and Y dot equals 0. So we have to find combinations of X and Y that satisfy both of those equilibrium both species. The obvious one is X and Y equals 0, comma 0. This is the trivial point where you don't have any of either species. The next point we can determine if we look at the X equation and we set Y to be 0. We have X equals 4. So we set this to be 0. To satisfy this thing in parentheses to be 0, then we have X equals 4. So we have X comma Y equal 4 comma 0. The next one we can solve for do the same in the second equation. We set here x to be 0, and we solve for this part here equals 0. That gives us y equals 5 and x equals 0. 0, 5. And the last one requires solving two linear equations, x, y. Basically solving for this stuff in parentheses equals 0 and this stuff in parentheses equals 0 is a system of two linear equations. So we can solve for x and y there by hand by solving for x in one and subbing it into the other, and then back solving for y. So here we have 2.5, 3.75. If you plug in any of these combination of numbers, it should set x dot and y dot to be 0. So we see here in this first set of terms, neither species is present. Here we have only species x present. Seems to be a delay on our, there it goes. Here we have only third equation, we have only species y present, and the fourth equation we have both species present. So we have in general these 4 critical points, all of them in the non-negative state space domain, and for this particular combination of parameters. And next thing we do, just like we did in the previous examination of the predator-prey model, is we evaluate the system, the linearization of the system at each of the critical points. Linearization again, we have u dot v dot equals the Jacobian times uv, where u of t is the perturbation of x around a particular critical point, and v of t is the perturbation of y around a critical point. So we take our nonlinear system, and just in the vicinity of the critical point we linearize it, and we see what the nature of the solution of that linear system is. So we need each of these partial derivatives that exist in our Jacobian, partial f, partial x. So coming back again, f is this right hand side here. So we take the derivative of this with respect to x, and we get 0.2, that comes from the derivative of 0.2x, minus 0.1x, that comes from the derivative of here, 0.05x times x is 0.05x squared, so 2 times 0.05 is 0.1, so we get minus 0.1x minus 0.02y, partial f, partial y equals minus 0.02x. And let me just back up a bit here. I want to rewrite the equations here just so before we do the partial derivatives, so it's clear where these are coming from. So let's just rewrite these equations. We have x dot equals x times 0.2 minus 0.05x minus 0.02y, and we have y dot is equal to y times 0.1 minus 0.02y minus 0.01x. So again, fx is the derivative of this thing in blue, which is f of x comma y with respect to x. So the derivative of that with respect to x, we have this first term here, 0.2x with respect to x. So we get, from that we get a 0.2. Our second term, if we multiply it through, we have our x times 0.05x is negative 0.05x squared. The derivative of that is minus 0.1x. And the derivative of this term, 0.02y times x, is minus 0.02y. Derivative with respect to x. Derivative of that same system with respect to y, well, this term, 0.2x, is 0 with respect to y, and minus 0.05x squared, 0 with respect to y. And we only have, if we multiply this x through here, we have minus 0.02xy. Derivative of that with respect to y is minus 0.02x. Okay, we'll do the same for the other equation. Ultimately, the numbers are different just because the parameters are different, but the idea is the same. Partial g partial x is minus 0.01y. and partial g partial y is going to be 0.1 minus 0.01x minus 0.04y. Now, this is our Jacobian. So our Jacobian ultimately looks something like this, equals 0.2 minus 0.1 x minus 0.02y. The second term is minus 0.02x. It comes from the coupling. And our off diagonal term down here is minus 1y. And our other diagonal term is minus 0.1, or is 0.1 minus 0.01x minus 0.04y. If we have no coupling, we have a purely diagonal system. The coupling comes in the off diagonal terms. Those minus 0.02 and minus 0.01 were originally these parameters, b1 and b2 in the system. If b1 and b2 are 0, we have no off diagonal terms. Jacobian looks like this, and then what we do is evaluate this at each of the critical points, producing a constant matrix from which we can derive the eigenvalues. At the point 0, 0, for example, we have lambda 1. Well, we have, if we plug in x equals 0, y equals 0, all these terms are gone, right? Except for those two constant terms. So our Jacobian looks like, our Jacobian looks like this, equals 0.2, 0, 0, and 0.1. And these are just the growth rates of those two species. The logistic terms, or the density dependent terms, do not play a role here because we're at the origin. We're very close to extinction of the species. There's no way that the density dependent terms should matter at this point in terms of what the system's doing. And the coupling terms don't matter as well because we're very near the origin. So the amount of both species is so small that they're essentially not competing with each other. So we have the simple diagonal system. Again, we could pick off the eigenvalues. They're both positive in this case. Here's lambda 1 and here's lambda 2. So we have 0.00 gives lambda 1 comma lambda 2. This is the easy one to do, equals 0.2 and 0.1. So this is a nodal source. And we have 0, comma 5. So noting a potential problem in the lecture notes. 0, comma 5. Check this afterwards. Lambda 1, lambda 2. We have 1 positive and 1 negative. At 4, comma 0, we have lambda 1, comma lambda 2. Again, 1 is positive, 1 is negative. And we have at point 2.5, 3.75, our interior point, we have lambda 1, lambda 2 equals minus 0.05, minus 0.15, both negative. So this one here is a saddle point. This one here is a saddle point. One is positive, one is negative, both real. This interior critical point here is a nodal sink. Both eigenvalues are real and negative. I'll draw the solution and then we'll talk a bit about what's going on. If you actually draw the solution, it looks like this. Now we can already start to sketch it out a little bit, knowing something about these critical points. So we have 4, comma 0, 0, comma 0. We have this one here at 2.5, 3.75, and we have up here 0, 5. So there's our 4 critical points of the system. This one we have, if we only have species X, it grows exponentially. Species Y, it grows exponentially. But both eigenvalues are positive. So anywhere from here, it's going to grow exponentially away from the origin. Here, we have, if we only have species species X, this is the density-dependent carrying capacity. 4 is the carrying capacity of X. So the solution along the x-axis with no y present will be attracted to that point for 0. Critical points. Same goes for species Y. Along the y-axis, if we only have y, the solution is going to be attracted towards the y value of 5, which happens to be the carrying capacity of our y species. And at this critical point, the interior critical point is a nodal sink. All solutions in the vicinity that are attracted to that particular solution. Now, going back to these 2 previous critical points, a saddle point has stability along a single axis. In the case of this critical point here, it's only along the x-axis. Along any other axis, it is unstable. So now we can start to draw what the system looks like. And I'll draw general solutions, so I'll leave those sort of perturbations as they are, and I'll draw general solutions in green of the system. So everything's ultimately attracted towards this critical point here. With the exception of solutions that were exactly either x existing or y existing. Or only y existing. If you started with an initial condition of x, of some combination of x and y, both being finite, any of those solutions are drawn towards this critical point right here in the interior. It is stable, and it represents a stable equilibrium of the system. What we're going to do in lab on Thursday is we're going to plot up this solution, and then we're going to start playing with the parameters. What happens when you increase competition, for example? So if competition becomes the dominant terms of these equations, what's going to happen to it? You can think about that. And then we'll also give advantage we'll give advantages to one species over the other. It will be a better competitor. It might be a faster grower, or some combination of the two. What happens in that case? And you can imagine what's going to happen in that case. So ultimately, we may not have, this point here may not be stable. It might be unstable. And ultimately, we'll find that we may not have this point existing at all. So if you determine a critical point, and that critical point has has negative values, then it's not a valid critical point. For this biological system, it must have positive values to be valid, or I should say non-negative values to be valid in the phase plane. And we'll see what happens as we begin to modify these terms. It's going to change the solution structure as we give advantage to one species over the other, or perhaps just simply increase the competition to a level where they're just simply competing rather than focusing on their own growing. So we'll pick up on that on Thursday. That's it for this section.